Hello and welcome to all students. In this lecture, we learn about the differentiation, gradient of scalar valued function, and we see the algebra of gradient of scalar valued function. Algebra of gradient of scalar valued function. Okay. So, uh, in the last lecture we saw some definitions, examples, some remarks. Now in this lecture we study about the algebra of gradient of scalar valued functions. Okay, so let us go to the slide number 12. Okay, so here we find all the algebra of gradient of scalar valued function. So let capital S be a non-empty open subset of Rn, and let A belongs to S, and suppose gradient of F and gradient of G both exist at point A, then gradient of F plus G exists at point A. First identity says that gradient of F plus G means addition of gradient of two functions. Addition of gradient of two functions means, or we can say that addition of gradient of addition of two functions, gradient of F plus G exists at point A, and gradient of F plus G at A is equal to gradient of F at A plus gradient of G at A. Second identity says that gradient of F minus G exist at point A, and gradient of F minus G at point A is equal to gradient of F at A minus gradient of G at A. And third identity says that gradient of alpha f exists at point A, and gradient of alpha f at point A is equal to alpha times gradient of f at A. Fourth identity says that gradient of f into g exists at point A, and gradient of f into g at point A is equal to f of A into gradient of g of A plus g of A into gradient of f of A. So this is the product rule in the case of derivative. So it is similar to the product rule in the case of derivative. Okay. So now fifth identity says that gradient of f upon g exists at point A, and gradient of f upon g is equal to g of A into gradient of f of A minus f of A into gradient of g of A whole divided by g of A square, provided that g of A not equal to 0 in the neighborhood of A. So these are the identities, or we can say that these are the algebra of gradient of a scalar valued function. Okay, so all these identities we will prove one by one. So first consider the first identity 1. Let capital S be a non-empty open subset of Rn. Let A belongs to S, and suppose gradient of f and gradient of g both exist at point A, then gradient of f plus g exists at point A, and gradient of f plus g at point A is equal to gradient of f of A plus gradient of g of A. So this identity we can state in other words. So gradient of addition of two functions is equal to addition of their gradients. So this is also another statement or another way to state this identity. So let us write the proof of this theorem as given that gradient of f and gradient of g both exist at point A, as given that gradient of f and gradient of g both exist at point A. Therefore we can say that partial derivative of f with respect to xi at point A and partial derivative of g with respect to xi at point A both exists for all I is equal to 1, 2, 3 up to n. Therefore we have partial derivative of f plus g with respect to xi at point A is equal to partial derivative of f with respect to xi at point A plus partial derivative of g with respect to xi at point A exist for all I is equal to 1, 2, 3, up to n. So this second step is nothing but partial derivative of addition of two functions is equal to addition of their partial derivatives. So these partial derivatives exist means partial derivative of addition of two functions with respect to all variables exist. Therefore the vector with n components, partial derivative of f plus g by dou xi, dou f plus g by dou x2 x2, dou f plus g by dou xn. So this vector with n components also exist, and therefore this vector is nothing but gradient of f plus g at point A exist. Okay, so this is the first part of this identity. Here we have proved that gradient of f plus g at point A exists. Now we will prove the main identity, gradient of f plus g at point A is equal to gradient of f plus g at point A is equal to gradient of f of A plus gradient of g of A. That we will prove in the next slide. So now consider the left hand side, gradient of f plus g at point A equal to, so by definition of gradient of scalar valued function, gradient of scalar valued function is nothing but a vector quantity with n components, and each component is nothing but I, and ith component of this vector is nothing but the partial derivative of that function with respect to ith variable. So our first component is nothing but partial derivative of f plus g with respect to x1. Second component is nothing but partial derivative of f plus g with respect to x2, nth component is nothing but the partial derivative of f plus g with respect to xn. with respect to xn. Now we know that as we know that the partial derivative of addition of two functions is equal to addition of their derivatives. So each component we will split into the two partial derivatives. Okay, each component we will write as addition of two partial derivatives. So first component is nothing but addition of partial derivative of f with respect to x1 plus partial derivative of g with respect to x1. Second component is nothing but addition of partial derivative of f with respect to x2 and partial derivative of g with respect to x2. Similarly, the nth component we can write as addition of two partial derivatives, that is partial derivative of f with respect to xn plus partial derivative of g with respect to xn. This implies that dou f by dou x1, so this vector is nothing but the addition of two vectors. So first vector is dou f by dou x1 at a, comma dou f by dou x2 at a, comma dot 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 dou f by dou xn at a, plus the blue vector is dou g by dou x1 at a, comma dou g by dou x2 at a, comma dot 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 comma dou g by dou xn at a. So first pink color or magenta color colored bracket is nothing but gradient of f at point a plus gradient of g at point e. Thus we proved that gradient of f plus g at point a is equal to gradient of f at a plus gradient of g at a. Gradient of f plus g at point a is equal to gradient of f at a plus gradient of g at a. So thus we have proved the first identity. Now similarly we can show that gradient of f minus g at point a. Similarly we can show that gradient of f minus g at point a is equal to gradient of f at point a minus gradient of g at point a. Okay, means gradient of subtraction of two functions is equal to subtraction of their gradients. So this identity we can prove say as similar as the previous identity. Now let us we prove the third identity. Identity third. Let capital S be a non-empty open subset of Rn and let A belongs to S. A belongs to S. And suppose gradient of f exists at point A, then gradient of alpha f exists at point A and gradient of alpha f at point A is equal to alpha times gradient of f of A. Okay, so once again the identity is gradient of alpha f of A is equal to alpha times gradient of f of A. Proof for this identity, so first of all we show that gradient of alpha f exists at point A. Okay, so as given that gradient of f exists at point A, Therefore, as gradient of f exists, therefore the all components of the vector of gradient of f, dou f by dou xi at point A exist for all I is equal to 1 to n. Therefore, partial derivative of f with respect to xi at point A exist for all I is equal to 1 to n. So as partial derivative of f with respect to xi exists, therefore its scalar multiple function alpha f, its partial derivative. So partial derivative of alpha f partial derivative of alpha f with respect to xi also exists for all I is equal to 1 to n, and therefore if we make the vector with by taking these partial derivatives as a components, then what we have is a vector with n components, dou alpha f by dou x1, dou alpha f by dou x2, and comma dot 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 comma dou alpha f by dou xn. This vector also exists, and as this vector exists, this vector is nothing but gradient of alpha f at point A, and this exists. So the first part this is the first part of this identity. So let us prove the main part. Consider gradient of alpha f at point A. Okay. Now consider gradient of alpha f at point A is equal to gradient of alpha f, partial derivative of alpha f with respect to x1, comma partial derivative of alpha f with respect to x2 at point A, comma dot 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 partial derivative of alpha f with respect to xn at point A. So uh, these are the partial derivatives of alpha f function. So from all these partial derivatives we can take outside constant alpha or scalar alpha. Then we have a second step, alpha into dou f by dou x1 at point A, comma alpha into dou f by dou x2 at point A, comma dot dot dot, comma alpha into dou f by dou x alpha into dou f by dou xn at point A. Now let us take alpha common, or let us take alpha outside of this vector. Okay, each component has alpha, therefore take outside. So alpha inside the bracket dou f by dou x1 at A, comma dou f by dou x2 at A, comma dot dot dot, comma dou f by dou xn at A. So alpha into this bracket is second last step, the bracket is nothing but del f of A. So finally we have proved that del alpha f at A is equal to alpha times del f of A. By using the rules of differentiation and partial derivatives, we can prove the remaining identities. So fourth identity is gradient of f into g exists at point A, and gradient of f into g exists at point A, and gradient of f into g at point A is equal to f of A into gradient of g at A plus g at A into gradient of f at A And fifth identity says that gradient of f upon g exists at point A, and gradient of f upon g, gradient of f upon g is equal to g of a into gradient of f of a minus f of a into gradient of g of a whole divided by g of a square. So in this way all the identities we can prove. So these two identities are homework to you to prove these identities. Okay, so let us stop our here our lecture is over and we stop here. Thank you very much.